Today what I want to talk about is measurement and measurement reliability. Before we start that discussion, which is detailed for you in Supplement 1, are there any questions about the material that we covered in the last couple of meetings, so measures of central tendency and measures of variation? Either in what those things are conceptually or in how to go about computing those statistics. You're all comfortable? I can see it now on the course evaluations. He is the most insightful instructor I have ever had. I get everything the first time he goes through it. Let's then talk about measurement reliability. Measurement reliability, in a fundamental way, has to do with the consistency of scores. There are two general issues surrounding measurement. One of them is measurement validity. And measurement validity has to do with the accuracy of scores. Are you measuring the thing or those things that you seek to measure? Does the SAT really measure scholastic aptitude? Do tests of intelligence really measure intelligence? Do tests of extroversion really measure extroversion? Or are they measuring something else entirely, or are they in part measuring something else? That has to do with the accuracy of the integrity of the measure relative to the construct that it purports to measure. But it also has to do then with the accuracy of the scores that that measure generates. Yes? And that is a matter of measurement validity, and we will not talk about that in detail at all, at least today. What I want to focus on today is a preliminary issue to measurement validity, and that is measurement reliability. And measurement reliability does not deal with the accuracy of scores, does not deal with the issue of whether measures of intelligence are actually measuring intelligence. It deals simply with the consistency of scores. And one way to envisage this is consistency across time. For example, if I were to administer a test of arithmetic ability at the beginning of a course in arithmetic, some form of arithmetic, and then I administer a second test of arithmetic ability in that same class, if the scores are reliable, then people who scored toward the top of the distribution at time 1 should score around the top of the distribution at time 2. And people who scored toward the bottom of the distribution at time 1 should score toward the bottom of the distribution at time 2. If scores are inconsistent, so if the measure has low reliability, the very opposite should happen. That is, people who scored relatively high at time 1 should score lower in the rank ordering at time 2, and people who scored relatively low at time 1 should score relatively higher at time 2. If measures are reliable, then the time 1 score is predictive of the time 2 score. It tells you something about the likely score at time 2. If measures and so scores, observed scores, are unreliable, then the time 1 score does not provide predictive value. That is, it does not help you predict or the score, a person's score at time 2. If you have been in classes where your rank position in the class has fluctuated dramatically across the same form of testing, it is likely that one or more of those test forms was unreliable. If your position, however, remains relatively consistent, then it suggests that the tests, and so that is the measures, and so the observed scores, were relatively reliable. Okay. Our arithmetic ability does not, without divine intervention of some kind, does not change from one day to another. Our reading ability, unless there's some sort of divine intervention, does not change dramatically from one day to another relative to the ability of others. The same is true of what are seen as personality attributes like introversion, extroversion, self-consciousness, need for achievement, sensation seeking, and so on. So measurement reliability has to do with consistency in scores. If I get on my scales in the morning at home, my bathroom scales, and I look down and it says 182 pounds, how much do I weigh? If, as happened, I'm driving merrily along the street in my wonderful piece of Japanese engineering, and I see that blur of colored lights in my rear view mirror and that woo, woo, woo. And the first question the cop asked me is, do you know how fast you were traveling? Well, no, I don't. Who's going to say, yeah, I was doing 95, you know, officer, and I knew it. Let's just say I was going faster than the speed limit. He said, I caught you twice doing, and I don't want to tell you how fast I was going. Let's say I was doing 85 miles an hour in a school zone. No, I wasn't. No, I wasn't. Let's say I was doing 85 miles an hour on 290 in a 65 mile an hour zone. Let's say I was clocked at 85 miles an hour. How fast was I actually going? If I look at my watch and it says 11:48 and 25 seconds, what time is it really? You don't know? Is this a mysterious question? Is it like, well, or is the question or the answer to my questions, are they so obvious that you can't even be bothered saying? Let's go back to me, the car, and the cop. The highway patrol officer. The highway patrol officer told me I was doing 85 miles an hour. How likely is it that I was actually doing 85 miles an hour? Very likely. Let me show you a trick. This is not a trick. Let me show you the world. There are available to us observed scores. Those observed scores could be scores of any kind. Miles per hour, our height in feet and inches, the time on our watch, the temperature on our thermometer. We are surrounded by observed scores. We can also talk about true scores. And that's the question that I'm asking now. If I'm clocked at 85 miles an hour, how fast was I actually going? If the observed score was 85, what's the true score? And we tend to treat observed scores as if they equal true scores. We're forced into this position, typically, at least in our naive world. We're forced to treat observed scores as if they are true scores. But observed scores do not equal true scores. Observed scores equal true scores plus or minus some amount of error. And I can't say that word any other way. Error. To me, it's just error. Observed scores equal true scores combined with some amount of error. You know this. You know this because you've had a watch that gains time. You've had a watch that loses time. You've had a thermometer. You've had a set of bathroom scales that some days appear to weigh you at 182, and the next day it's 187, and the next day it's 181. That's an indication to you of inconsistency, and it is most probably an indication of measurement unreliability, because what is fluctuating is not your true score. Your body weight is likely to change minimally over the course of 3 days. So what is changing is the error component of your observed score. And error can be of two kinds. Error can be systematic. Some of you know that your bathroom scales are affected by systematic error. You know this because one morning you got on your scales and it said you weigh 182 pounds, and you went down to a physician's office where they've got those elaborate and fancy scales that would cost you like $1 million, and you stepped on there and it said you weighed 184 pounds. And on another day you got on your bathroom scales and it said you weigh 180 pounds, and you went to the same physician's office and got on the same scales, and those scales said you weigh 182 pounds. The error component, would you agree, is consistent. It's systematic. It's always a difference of 2 pounds. Your bathroom scales always measure you 2 pounds lighter than the physician's scales. And let us suppose, unrealistically, let us suppose that the physician's scales are error-free, that they generate only true scores. If you now, on a third day, step on your bathroom scales and it says 184 pounds, and you're headed out to the physician's office, what will the physician's scales say you weigh? 186 pounds? Yes? Because your scales consistently have weighed you 2 pounds less than the scales in the physician's office. The error involved in the observed score, and now I'm talking about the observed score from your bathroom scales, the error involved in those observed scores is systematic. That is, it's always of the same magnitude, and it's always in the same direction. It's like having a watch that's always 5 minutes slow. It's like having a thermometer that always generates a body temperature 1 degree above your actual body temperature. It's like having a speedometer that always measures your rate of ground speed 3 miles an hour higher than it actually is. If you have a speedometer that measures your ground speed 3 miles an hour higher than it actually is, and you know this from experience, if you now look at that speedometer and it says you're going at 50 miles an hour, you know what your actual speed is. It's 47 miles an hour, because that instrument generates observed scores that are affected, again unrealistically, only by systematic error. The error is always of the same magnitude and always in the same direction. Systematic error affects measurement validity. Systematic error affects measurement validity. If an instructor says something more than once, it's a fair sign it's going to be on an exam, or it's important. If you take a gun and aim it at a target, and the bullet hits the target 2 inches to the left, immediate left of the center of the target, and you move to a second target that is the same size and has the same form as the first target, and you again aim at the center of the target, and you again miss the center of the target by 2 inches to the left, the weapon you're firing is affected by systematic error, because the miss is always in the same direction and it's always of the same magnitude. Error can also be random. You get on your scales at home. They weigh you at 182 pounds. You go down to the physician's office. You get on the scales there. They weigh you at 185 pounds. You get on your own scales at home. They weigh you 181 pounds. You get on the scales at the physician's office, they weigh you 179 pounds. You get on your scales at home, they weigh you 180 pounds. You go down to the physician's office, they weigh you at 182 pounds. You now get on the scales a fourth time and you measure, and your scales indicate that your weight is 184 pounds. What is your true weight? Again, assuming that the physician's scales generate only true scores. You have no idea. You have no idea. Because the error is random. Sometimes the physician's scales weigh you heavier than your home scales, and sometimes they weigh you lighter than your home scales. Sometimes the difference is 3 pounds, sometimes it's 2 pounds. You have no idea of the direction or the magnitude of the error. And so you're unable to predict your true score. You're unable to calculate your true score. Because the error is random. Random error changes in direction and it changes in magnitude. Random error fluctuates in direction and in magnitude. Sometimes it's positive, sometimes it's negative, sometimes it's a small amount of error, and sometimes it's a large amount. And random error is at the root of measurement reliability. Let me say something as we go along here. In reality, all observed scores, whatever instrument you use to generate those scores, whether they're academic tests, whether they're mechanical measurements, no matter whether it's Big Ben, and goodness knows there is no better measure of time than Big Ben. Whatever the scores that are generated by any measurement, the instrument and the scores are affected by both systematic error and random error. In reality, observed scores include both systematic error and random error. For our purposes, we've assumed at times that observed scores include either systematic error in some of the examples I offered or random error in some of the other examples I've offered. I'm simply pointing out that our discussion does not represent the real world. In the real world out there, in the world that we bring in here, all observed scores include both systematic and random error. The objective of the researcher is to minimize the amount of error that's contained in observed scores. The objective of the researcher is to minimize the amount of error contained in observed scores. Where does random error accrue from? What are the sources of random error? While you're thinking about that, I'm going to make a phone call, if that's all right. You know. It was not a rhetorical question. Didn't I say that when it was not a rhetorical question, I'd make a sign? This is not a rhetorical question. Where does random error come from? Let me go back a step. Let me go back 2 steps. Let me go back 3 steps. We can make a dance out of this. First of all, observed scores invariably include both systematic and random error. So second, the objective of the researcher is to minimize the systematic and random error contained in observed scores. We're going to forget systematic error for the moment because it influences measurement validity rather than measurement reliability. So now the issue is random error. the fluctuation in observed scores. Let us assume that I'm administering a test of arithmetic ability to each of you. Would you agree that somewhere up here you have a true score? You have a true level of arithmetic ability. I can't even get consensus on this. Believe me, it's the nature of the world. Up here, somewhere, you have a level of true arithmetic ability. Who knows what scale it's measured on, but when you get to St. Peter, you'll find out. It's height, weight, arithmetic ability. In a frequency distribution, because as I recall, St. Peter is French. I remember what I say, even if you folks don't. Which is, it's good that one of us remembers at the moment. Okay? We're all just cycling along, right? Just cycling along. Why would you score 82 out of 100 on one test of arithmetic ability and 87 out of 100 on another test of arithmetic ability and 79 out of 100 on a third measure of arithmetic ability?
I mean, it's all dependent on what the score is. I mean, because everything's random. It's all dependent on something else.
No.
Yeah.
No. It's not all random. If it were all random, you and I would stay at home. We'd barricade ourselves in our houses. You know, if it were all random, we would never venture out. We could never talk with certainty about anything. The cop stops you and says, I clocked you at 85 miles an hour. You'd say, no, because that's random. Any number could have appeared on your radar gun. I was actually traveling at 4 miles an hour. So it's not all random, if I understood you correctly.
Well, it's all dependent though on something else, isn't it? I mean, if you're talking about like the random scores, I mean, if the person who's like looking at it, or if like, say if it's a scale, the scale could be broke, or the person researching it could be like, I don't know, they could be tired or something.
We're not talking about, you're getting, so you're pitching stuff out there and some of it's sticking. You know, this is like playing roulette. I'll play 28, 21, 19. The 19 came in. I got to finish over here. I'll get to you. I got to finish over here. We're not talking about measures that are broken. We are talking about measures that generate that generate false observed scores. And we've limited that discussion to instruments that generate false scores because the scores they generate have been infiltrated by random error. You talked about somebody could be tired. That is a source of random error. Because if I administer a test of arithmetic ability to each of you, some of you will feel really perky. You've done your crack in the morning, you've done a line of cocaine, and you've sucked down 14 cups of Starbucks, extra caffeinated. You're feeling pretty perky. Others will have been awake all night studying. They will their 8-year intimate relational partner will have called them in the middle of the night to tell them it's all over. And they'll run over their pet cat when they're leaving the house. By the time they get here, they're feeling pretty tired. But that you understand, some of you will feel pretty perky, some of you will feel relatively perky, some of you will be neither perky nor fatigued, that blissful state. Others of you will feel relatively tired, and others of you will feel extremely tired. That is, fatigue doesn't distribute itself equally across the group, so that you will not be equally affected by fatigue. So fatigue, respondent fatigue, is a source of random error. Let me ask you this. If the objective of the researcher is to minimize random error, and if respondent fatigue is a source of random error, can the researcher control that?
You could try to.
You can try to. You can give respondents instructions to behave in a particular way, to get a sufficient amount of rest. This is why when you're scheduled to have specific sorts of tests at the physicians, you often get a sheet of instructions on how to behave, because if you don't behave in that way, the results, the scores that the tests generate will not be valid. They will be affected largely by random error. Because some of you will abide by the instructions, some of you will violate the instructions in one way, some of you will violate the instructions in another way, so that your observed scores are influenced by random error. If we go back to the issue of fatigue, the administrator of the test, this semester me, can encourage you not to study the night before, can encourage you to get sufficient sleep and rest. But I cannot follow you home. Well, I could, but I think that's called stalking. I cannot follow all of you home. I can follow one or two of you home. I can't, no. More seriously, I cannot follow you home. I cannot ensure that you adhere to the instructions I have given. The point I'm making is that respondent fatigue is, first of all, a source of random error, and second, it's not under the control, the direct control of the researcher. Given that, do you understand that even at this preliminary stage, that observed scores always involve random error? Because typically those observed scores are generated by participants whose scores are affected by the level of fatigue they have. Are there any other sources of random error? You were going to ask a question or make a comment. You forgot? What you're saying is, Douglas, you talked for so long. You ignored me for so long. I'm not going to hold a grudge. But should I meet you outside, don't expect me to talk to you. Right? This is what happens in conversations with others. The other person talks so long you forget what you were going to say, and it's like, what the hell? I give up. What might be some other sources of random error? How about the length of the test? Each time you go to a new physician, you get 17 pages to fill out. They ask you to show up 30 minutes early. Actually, you need to be there an hour and a half early, because it's now 17 pages of questions that you have to answer about your health. You start responding to that, and on page 1 you're really giving it some thought, you know. Have I ever had TB? No. Have I ever had polio? No. By the time you get to page 17, you don't care anymore. Have you ever been in the hospital? I don't know. Yes, of course I have. What were you in the hospital for? Oh, I broke my back, you know. I broke a leg, I broke an arm, I had spots coming up, fearsome things all over my face. By the time you get to page 17, you don't care. You participate in a study for extra credit, or because you're being paid $3 by the Baylor School of Medicine to show up every week for 19 consecutive weeks. It's a 28-page questionnaire, and it's filled with those scales where there are statements, and then there's a 5-point scale. 5 through 1 describes me very well, doesn't describe me at all. And when you start, you read the first statement carefully and you give it some thought, and yeah, that's pretty a 4. And you read the second statement pretty carefully and you say, no, that's really not me. That's not me, a 1. By the time you get to page 6, you are circling 3s so quickly that it's just a blur of light, just to get to the end of the 28 pages. Test length affects observed scores because it introduces random error. Why does it introduce random error? Because some of you will reach that point of, let me just circle the 3s on page 2, others of you on page 9, others of you on page 21, others of you not at all. So it's a source of random error. The problem is that test length functions to influence measurement reliability in quite an opposite way as well. That is, as a rule of thumb, the longer the test, the more reliable it is. That is, the more items on a test, the more reliable it is. The fewer items on a test, the less reliable it is. The least reliable measure in the world is a single item measure. If you're trying to market a candy bar and you give it to a pilot group, this seems to be a very, very straightforward task. If you want to know how much people like the candy bar, why not just ask them how much they like the candy bar? First of all, because people define liking in different ways. Second, because they could have liked different things about the candy bar. Some people might have liked the chocolate on the candy bar, others the caramel, others the peanuts, and others the wafer. Why do you put wafers in candy bars? I have no idea. Caramel I'm not really up on either. The chocolate and the nuts I understand. Third, liking for a candy bar is not necessarily predictive of whether you will buy that candy bar. You may not buy that candy bar because you're sensitive to your weight and you think that eating candy bars will make you gain weight. You might not buy the candy bar that's being tested because you already like 4 other candy bars much more than you like this one. You might not buy the candy bar because you don't like the name of the candy bar. If the candy bar is called nasal content, you're unlikely to buy the candy bar. I can't speak for anybody else, but I'm unlikely to buy the candy bar. I just can't go into a store and say, could I have a bar of nasal content? When I can say so easily, could I have a Snickers bar? Yeah. Snickers sounds fun, you know. It sounds almost childlike, almost like a grin, a laugh. So nasal content is never going to compete. You may not buy the candy bar because it's overpriced in your mind. You can't. The point I'm making in a heavy-handed way is that single item measures, even when the task appears straightforward, are likely to generate highly unreliable scores. So you've got a contradiction here. On the one hand, we've discovered that fairly lengthy tests are preferred over relatively short tests, because all other things being equal, the more items on a test, the more reliable the test. Because the effects of any unreliable items are minimized, because they're likely to be embedded by a large number of reliable items. But we found at the same time that respondent fatigue increases measurement unreliability. And the longer the test, the more likely it is that the respondent will at some point become fatigued and then generate data at some point that lead to unreliability, random error in the scores, and so leads to measurement unreliability. Test length is under the direct control of the researcher. So test length is controllable, whereas respondent fatigue is not controllable. Measurement unreliability also accrues from the ambiguity of the items. You know this. You know this because I suspect most, if not all of you, at some point have gone to an instructor and said, I could have done better than an 82 because there are these 3 items that were ambiguous. I didn't know whether you were asking for this or for that. And if getting a question right or wrong comes down to flipping a coin, some of you are going to flip heads and some of you are going to flip tails. And if heads leads you to the right answer and tails to the wrong answer, this ambiguity has not affected all of you in the same way. Some of you have benefited and got the right answer, and some of you have been penalized and got the wrong answer. So item ambiguity is a source of random error. And clearly this is, to a large extent, under the control of the researcher. The last source of random error that I want to identify is respondent mood. The mood of the respondent. when we have exam 1, some of you are going to show up so happy, it's like ecstasy. Some of you are going to show up sort of happy. You know, your pet cat was there in the morning, reported present and correct. There were still Cheerios left in the packet, and there was still milk to have with it. There was a little bit of orange juice left. Oh, things are okay. Your car started, not much traffic. You played some good music on the way here, so you're sort of happy when you show up. Some of you will show up neither happy nor unhappy. Again, that blissful state of perfect equilibrium. Some of you will show up relatively unhappy. You hit bad traffic, there were no Cheerios left in the box, and besides, the milk had gone off. You're relatively unhappy. Some of you will show up seriously unhappy. The cat did not report present and correct. There weren't any Cheerios in the box, but there was milk, which is even worse than having no milk and no Cheerios. Now you got milk. Actually, it's worse to have Cheerios and no milk, because at least you can drink the milk. So you've woken up, you've got Cheerios and no milk. You run over the cat who didn't report present and correct. By the time you arrive here, you're unhappy. Do you understand that, again, respondent mood varies across respondents, and so doesn't affect the observed scores in a consistent way. It affects observed scores in an inconsistent way, and so is a source of random error. Second, it is not a source of random error that the experimenter can control. One of the issues here is clearly to identify sources of random error. The other issue here is to indicate to you that some of those sources of random error can be controlled by the researcher, but some cannot. Therefore, all observed scores include a random error component. That is, all measures are to some extent unreliable. It does not make conceptual sense to imagine a perfectly reliable measure. Nuclear clocks do not provide are not a perfect measure of time. You have to periodically adjust those nuclear clocks. So even the most sophisticated measures include components of random error. Let's talk about reliability in a particular context. Let's talk about test, retest reliability. Test, retest reliability. The format of test, retest reliability is this. You administer a test of something at time 1. And to a group of participants. You administer a second test at time 2 to the same group of participants. Let's say you're measuring arithmetic ability. This means that you administer a test of arithmetic ability. Let's say the test involves 50 items. you administer the 50-item test of arithmetic ability at time 1, and then you administer to the same respondents a test of arithmetic ability at time 2. That second test should include the same number of items that were involved in test 1. In order to maximize consistency, one could argue that you should simply administer the same test at time 2. Yes? I was just wondering if anybody was in the room with me. If reliability has to do with consistency and inconsistency, then surely the most consistent thing to do is administer the same test at time 2 that you administered at time 1. The problem is that people learn. They learn from their mistakes. They talk about the test. What was your answer to number 4? 18, option B. Oh really? I thought it was option C, 22. Oh, I got that answer first because I forgot to do this certain operation. Then the person who got the question wrong the first time is likely at the second point to recall why she or he got it wrong, correct their mistake and get the question right. Not because they have any increased arithmetic ability, but simply because they learned the problem that they had encountered, learned where they had gone wrong from somebody else who took the test. What researchers often do then is they generate a large number of items, in this case a large number of items designed to measure arithmetic ability. They create a pool of items. They reach randomly into that pool of items and pull out some number. We've said 50. And those 50 items comprise test 1. They then either throw those 50 items away and reach into the pool again and pick out 50 other items, all of which cannot have appeared on the first version of the test, and they use those 50 items as test 2. An alternate strategy is to reach in the first time, get those 50 items, use those as test 1, collect those 50 items up, throw them back into the pool, swirl the pool around and pick out 50 items randomly. And use those items for test 2. There is now some probability that one or more of the items that appeared on test 1 will appear on test 2. Do you agree? This is what people at Princeton do for the SAT and the GRE and the GMAT. They have a large pool of items. They throw the questions from one test back into the pool, and they select from the pool again. This is replication with or without substitution. So we have scores on test 1 and we have scores on test 2. A test of arithmetic ability. If person A scored high at time 1 and person B scored low at time 1, and this is a reliable test of arithmetic ability, what would you predict about the scores of persons A and B at time 2? Would you predict, if it's a highly reliable measure, that person A will score high at time 2, moderately at time 2, or low at time 2? All those who would predict that person A, if this measure is reliable, will score high at time 2. The rest of you are wrong. The rest of you are wrong. If it's a reliable measure, then it's generating consistent scores. So that persons who scored high at time 1 will score high at time 2, low at time 1, low at time 2. If, however, the instrument is relatively unreliable, then you have no way of predicting person scores at time 2. Are there any questions? Are there any answers? This is an exciting tale. This is a mystery. Hang on a second. I will get to you, and remember, write it down if you need to, what you were going to say, because I don't want anybody else forgetting and then holding it against me forever.
Okay.
You know, it's a threatening enough world as it is without having... Now I've forgotten what I was going to say. This is a thriller-diller of a story. We've got to the last 40 pages. We need to discover how you go about measuring reliability, how you go about measuring test-retest reliability. That explanation is, together with the rest of this information, although not the interpretation, available in the supplement, Supplement 1. You should read through Supplement 1, and next time we will talk about how you measure test-retest reliability. You have a question or a comment?
Yeah, my question is with the time 1 and the time 2 and the A and the B and the reliability. You said that if the person A scored high on the test, then if it's a reliable source, then it's going to be higher the next time?
No. What I said was, if this is a highly reliable measure, then we can predict that a person who scored high at time 1 will also score high at time 2. Their score will fluctuate, and they may not be the highest score, they may not be in exactly the same rank order, achieve the same rank order, but they will score high at time 2. Likewise, if this is a highly reliable measure, somebody who scored low at time 1, we can predict will score low at time 2. If this is a highly unreliable measure, the score at time 1 provides us no information at all about the score at time 2, so that we will be unable to predict the score at time 2. If what you see in scores is that there is fluctuation in how persons perform across these two tests, this is evidence of measurement unreliability, because this is inconsistency, and when the observed scores are inconsistent, it's evidence that they've been affected by random error. It is evidence that the instrument used to generate those scores is unreliable. This is better than Temple of Doom and all that stuff, isn't it? It's like, wow, this is magic. This is a mystery. Okay? We'll finish this story next time.